Yeah, it's a pleasure to be talking to you. Thank you very much to the organizers for putting together this these 3 weeks. I'm really excited about lots of the talks. What I'd like to do in my lectures is to give a kind of introduction to this topic of 3D n equals to 4 gauge theory. It's a topic that has lots of interesting connections with the math side of the conference, particularly representation theory, also things like enumerative geometry. And so the idea is to give a kind of introduction to these topics with that in mind, to try to focus on things that that will allow us to kind of build a dictionary and maybe provide a stepping stone into those more advanced topics. So I'm very happy to answer your questions, and especially for those of you who are watching tomorrow at the watch party, please feel free to contact me on Slack. And I should also say that the Slack, I've put some lecture notes up in the Slack channel as well, so you can, if you prefer to follow along with those, they have a bit more detail. Okay, so then let me begin by giving an introduction or motivation for why we want to study supersymmetric field theories. So Aswin mentioned a couple of these things, but there are many connections between supersymmetry and supersymmetric quantum field theory and mathematics, geometry, representation theory. And so there are many ways in which they interact and they come together and they inform each other. But some underlying themes, I think, that that are important for these lectures and probably for the rest of the course are the following. So the first is a basic idea that supersymmetry ensures or allows you to have kind of exact moduli spaces of vacua. So spaces of vacua for your field theory that are exact, and also they carry interesting geometric structures. So they might have the structure of a Kähler manifold or a hyperkähler manifold, for example. And moreover, symmetries of your physical theory and quantum field theory are reflected in the geometry and the topology of those moduli spaces. So for example, it might be that you have a symmetry in your field theory, and that's reflected in maybe the isometries of the space. There might be an action of a group on the space, on the moduli space that you've got. Or in other cases, it might be that the symmetries encode the topology, in some sense, the homology groups of the moduli space. And so this is already the kind of thing that is the kind of setup that's important in, for example, geometric representation theory. You have interesting spaces with group actions on them. And so moreover, the kind of things, the kind of mathematical structures on top of those spaces that arise in representation theory also appear naturally from physical construction. So things like cohomology, K-theory, or even derived categories of coherent sheaves, things like that. So these things appear naturally in physical constructions. Okay, so that's my motivation. And so what I'd like to focus on in this talk is theories with what are called, well, they're in 3 dimensions, and they have a particular amount of supersymmetry called n equals to 4. And so I just want to spend a couple of slides focusing on why those 2 things are important. Why 3 dimensions and why this amount of supersymmetry. Okay, so first of all, supersymmetry. So we're interested here in theories that have so-called 8 supercharges. So they're sometimes called in 5 dimensions, you would call that n equals to 1. In 4D, you would call it n equals to 2. And in 3D, which is what I will talk about, they're called n equals to 4. And in general, these theories have a very intricate moduli space of vacuum configurations. And the geometric structure that they have can be very intricate. It can depend on a bunch of stuff. And in particular, it depends on the dimension of space. It depends on whether you're 5D, 4D, 3D, or so on. But they do have one common feature, which is that at least one piece of that vacuum moduli space, which is what we sometimes call the Higgs branch, and what I'll call X in my lectures, this is a space of a particular type, which is sometimes called a hyperkähler cone or a holomorphic symplectic cone. It's a kind of conical space. We draw a kind of cartoon like at the bottom of this page. And these type of spaces are kind of the really important in geometric representation theory. And they arise naturally in these types of, in this class of theories. So examples of these types of spaces are Nakajima quiver varieties, some slices in affine Grassmannians, nilpotent orbit closures, hypertoric varieties, moduli spaces of singular monopoles, many interesting spaces that I think that we'll hear about lots of those from different points of view throughout the 3 weeks of this course. So all of these interesting spaces arise in theories with this amount of supersymmetry. But my talk in particular will focus on 3 dimensions. So I should tell you what's special about that and why it's interesting. And in 3 dimensions, the special feature we have is that, well, supersymmetric gauge theories, at least, they're kind of distinguished in 3 dimensions in that they have 2 spaces. They have 2 branches or pieces of their moduli space, which are of this type, which look like these conical hyperkähler or holomorphic symplectic spaces. And so these go by the name of the Higgs branch, which I call X, and the Coulomb branch X prime. And so this is kind of this is great because you've got 2 of these spaces attached to any given theory. And moreover, there's an interesting kind of duality called 3-dimensional mirror-symmetry that exchanges the 2. And so what this means is that you can get interesting or surprising non-trivial relationships between mathematical structures associated to the 2 spaces. Physically, you can often take your theory and kind of view it from the perspective of the Higgs branch, and then ask the same question from the perspective of the Coulomb branch, where the computations might look very different, but the answer is exactly the same. And so this leads to kind of surprising connections between representation theory and enumerative geometry problems associated to these pairs of spaces. And that's a very active area of research. And I think there are going to be lots of talks about this type of thing. Okay. So that's my introduction. And with that, I'm in the rest of the lecture, I'm going to give an introduction to this class of theories. So maybe I can pause here to see if there are some questions already. And just to check that you can all hear me and I'm not talking.
None so far in the chat.
Right.
But,
okay.
And everything's going fine otherwise.
Great. Good to hear. Okay. So let me just begin then. And just to begin by set up some basic notation, just to make clear what we're working with. So I'm going to consider theories in flat space, 3 dimensions, Euclidean space, with coordinates x, and it's supersymmetry, so we're going to be working with spinors. So the spin group is SU2, and we have 2 component spinors that I have a kind of index alpha, and they transform. You can think of those as transforming in the fundamental representation of SU2. So just some standard notation, we raise and lower indices with some invariant tensors of SU2, and we have some Pauli matrices. Okay, so in any normal quantum field theory, then they're going to be symmetries, in particular symmetries of translations and rotations in Euclidean space. And they're generated by momentum, or their associated conserved charges are momentum and angular momentum that we can write as P and J. Now, in a supersymmetric theory, there are additional symmetries that go along with translations and rotations. In particular, there are some odds generators. There are some fermionic generators that I call Q, and they're fermions. And they're also spinors of SU2. So they have a spinor index, And the most general thing that I can do is to add n or curly n such generators. And they satisfy an algebra like this. So if I take the anti-commutator of the supercharges, then I recover the translations. So it's like a square root of the momentum operator. Okay, so the supercharges, they're spinors in space-time. And if I look at, this is just one piece, but if I kind of look at all of the commutators involving translations, angular momentum, and the supercharges, then they generate what we call the n-extended super Poincare algebra. So a really important idea in this talk, or what's going to come up again and again, is an idea of an R-symmetry. And the way to think about it is the following in this setup. Well, there's kind of a symmetry here. I said that I had n of these supercharges. Well, I can just take those and rotate them among themselves. So this is really the group of outer automorphisms of this algebra. And it just acts by rotations of on this index I of the supercharge that runs from 1 to n. And you see indeed here that the algebra depends only on delta ij, which is like the invariant tensor for On. And the connected component of this group, SON, rotations in n dimensions, this is what we call the R symmetry. So it's like it's a global symmetry of the theory. It's a symmetry that acts in a non-trivial way on the supercharges. Okay, so that's the Poincare superalgebra. So here I'm going to now make a specialization. You know, this was the general thing that I could write down. The thing that we're interested in is the case with n equals to 4 supersymmetry, when this number n is 4. And in this case, the R symmetry is SO4, which is also SU2 times SU2. And because there are lots of SU2s floating around, we give these labels. We give it a subscript H and C. So H will stand eventually for Higgs, and C will stand eventually for Coulomb. We'll see why that is in the course of the lectures. But because of this isomorphism between SO4 and SU2 times SU2, it's often convenient, instead of working with vector indices for SO4, to work with, again, spinor indices for the two SU2 factors. So I have indices A, B, etc. for SU2 Higgs, A dot, B dot, etc. for SU2 Coulomb. And so for the supercharges, instead of an index I, they now have a pair of these spinor indices. And 2 times 2 is 4, so there are four space-time spinors here, which is what we expect. And then the supersymmetry algebra can be written in this way. So all that's really happened here is I've replaced the invariant tensor of SO4 with the two invariant tensors of SU2 Higgs and SU2 Coulomb. Okay, so we'd like to build quantum field theories that have this symmetry. And so there are many types of theories that you can try to write down. For example, you might build sigma models, which are theories based on maps from space-time R3 into some other space. You might build gauge theories that display this, have this symmetry. And you might even try to consider non-Lagrangian theories, or maybe isolated theories that don't have a Lagrangian description. And in many cases, these different types of theories can be connected by either renormalization group flow or infrared dualities or things like that. But in the course of my lectures, I'm going to focus here on gauge theories. And gauge theories are kind of a fundamental starting point, and they have many connections with the kind of mathematics that we're interested in. Okay. All right. So my approach is not. I'm going to try and give. I'm not going to tell you exactly how one builds a theory of this type. But I'm going to try and tell you the data that you have to supply me in order that I can build a gauge theory. And kind of how that goes into building the types of fields that I have in my field theory. So there are two bits of data that you need to specify to give a 3D n equals to 4 gauge theory. And they're associated to what the gauge group is and what the matter is. So the first is a compact Lie group G, that's the gauge group. And then the matter is specified by a linear quaternionic representation of the gauge group. So what does that mean? It means that you have a representation of the group G that kind of acts on or acts by n quaternionic matrices or unitary quaternionic matrices. So it kind of acts on a quaternionic vector space of dimension n. So if you don't know what quaternions are or you don't like them, then I'm going to dispense with them in just a moment. So don't worry too much. This data kind of determines the spectrum of fields that I have in the theory. Sometimes we say supermultiplets for the representations of the superalgebra. And it also specifies, in this case, completely, essentially, up to some constants, the Lagrangian of the theory. In particular, it specifies vectormultiplets, which are associated to the gauge symmetry, and hypermultiplets, which are associated to the matter. And I should say, this is a good point to mention that many of the things that I talk about here will be very similar, if not the same, to what Madalena was talking about this morning in her lectures on 4D n equals to 2 theories. So I apologize if there's any overlap. Okay, so I said if you don't like quaternions, then we can get rid of them. So let's do that. So instead of working with quaternions, we can use this isomorphism where we replace SPN by what are basically 2n by 2n complex matrices, which are kind of simultaneously unitary and symplectic. And so another way to say that is that a quaternionic representation acts by symplectic unitary transformations on a complex vector space of dimension 2n. Now this is still fairly complicated, but in fact, in almost all, well, exclusively in what I want to say, almost exclusively in everything that I've done in my career, and I think for most connections to geometric representation theory, we want to specify to a particular class of representations, which are sometimes called cotangent type. And they're much simpler to describe. Instead of this fancy quaternionic representation, all we have to do is specify a unitary representation of G. So this is a representation where G acts by, the group acts by n unitary matrices. And then if you want to recover the quaternionic one in the previous language, you take that representation plus its conjugate. So R, that's like the cotangent bundle of R. And so that's why it's called a cotangent type. So if you like, you can forget all of this quaternionic stuff and just imagine that we specify a unitary representation of the group. Okay, I can see some comments in the chat, so I'm just gonna.
Yeah, but they're all irrelevant.
Okay.
Carry on.
I'll carry on. Okay, good. So so then if you like, we just need to specify a compact Lie group G and a unitary representation. And that will specify a theory for us. So let me tell you what fields we have. So I'm gonna be quick. Well, not quick. I'm gonna focus on the bosonic fields that we have in the theory. So the first is the vectormultiplet. The vectormultiplet depends only on the gauge group G, and it has the following bosonic fields. So first of all, there's a connection A on a principal G bundle. So that's just the gauge connection. We have a gauge theory, and that's it. But because of supersymmetry, we also have some scalar fields in the game. And the scalar fields transform first in the adjoint representation of this SU2C R symmetry. So here it has a pair of spinor indices that are symmetric. So that's 2 times 2 minus 1 is 3, which is the adjoint representation of SU2. And they also transform in the adjoint representation of the gauge group G. And then there are also some fermions that I'm going to skip over. So these are the fields that we have in the vector multiplet. We have a connection and some scalar fields in the adjoint. So here's the hypermultiplet. The hypermultiplet's the matter. That depends on this choice of representation. And again, it has some scalar fields and also some fermions. So I'm just going to tell you about the scalar fields. So first of all, they transform in the fundamental representation of the other R symmetry, the SU2H. And it transforms this time in the fundamental, the two-dimensional representation. And moreover, they basically they transform in the representation Q of the gauge group G. So if I'm working in components, I would have some fields phi with 2 indices. A is the SU2 Higgs index that runs from 1 to 2, and I is the symplectic index, and that runs from 1 to 2n. And then there's a reality condition on the fields. Okay, so again, if you don't like this quaternionic or symplectic stuff, then let's move quickly to more usual things. So we'll specialize to a cotangent type representation, just like before. And in this case, we can take this matrix of scalar fields, this 2 by 2n matrix, and we can kind of decompose it into n 2 by 2 blocks. Each of the blocks look like this right-hand side here, where the components of the blocks are now like complex scalar fields. So instead of working with these fancy things here with indices, we just have a pair of complex fields, x and y, and they transform in unitary representations R and the conjugate of R. Another way to say that is that if I take the pair of x and y bar, not x and y, but x and y bar, so that's like the first column of this 2 by 2 matrix, then that transforms in the fundamental representation of SU2 Higgs, and also in the representation, in the unitary representation R of the gauge group. Okay, so that was a bit of representation theory. And this specifies basically the content of your field theory, the bosonic fields. Okay, let me give you an example. So this was fairly abstract. Let me give you a very concrete example that's very important. So quivers or quiver gauge theories kind of give a very rich and interesting class of theories or ways to build gauge theories of this type. And so I'm not going to try and spell out kind of the full breadth of this type of theories, but just focus on a nice class of examples, which are called A-type unitary quivers. And so they're kind of represented by, well, at least physicists represent them by a picture like this. And in this case, the gauge group G is going to be just a product of unitary groups. So if you look in the diagram, each of the circles represents a gauge group, a unitary group. And together with that, we have to specify the matter. So the lines in this diagram will denote matter and encode the kind of hypermultiplet representation. And it does it in the following way. So if we first let V1 up to VL denote the kind of fundamental representations of the gauge group. So V1 is the fundamental representation of UV1. And then W1 up to L denotes some other fixed complex vector spaces of dimension little w up to WL, which transform trivially under the gauge symmetry. And then you take this representation R, so this is a theory of cotangent type. You take the unitary representation, which is given by the following formula. And the rule is whenever you see a line connecting two things, you should you add a piece to the representation, which is Hom from one to the other. So in particular, the lines along the top, they're the first pieces here, Homs from one group to the next, and then you have matter here. Another way to say that in more traditional physics language is that you've got a product of unitary gauge groups, you've got matter in the bifundamentals connecting them in sequence, and you've got W1 fundamental hypermultiplets, W2 fundamental hypermultiplets here, and so on and so forth. Okay. So the thing that kind of characterizes these things is that you only ever see representations that are kind of in the fundamental or anti-fundamental or bifundamental of the gauge group. Okay.
So Matt, there's one question in the chat.
Okay.
Can you comment on the central charges both in the SUSY algebra and in the context of gauge theories?
Yeah, thank you very much. So actually, central charges is the topic of tomorrow's lecture. So I'm going to discuss them in detail then. Yeah, actually, I've done a small thing here, and I've brushed over that there is a central charge kind of off shell in the gauge theory, but I'm going to discuss that in a lot of detail next time. So next lecture will be about central charges, introducing mass and FI parameters and things like that. Is that okay?
Yeah.
Great. But yes, they are there. They can be there, and they're important. In fact, they're super important. Okay. Good. So the next ingredient that I'd like to talk about is flavor symmetry. And so we've already talked about R symmetries, and R symmetries are symmetries that that kind of transform the supercharges in a non-trivial way. Flavor symmetries, on the other hand, are symmetries that commute with the supercharges, and so they basically commute with everything in the super Poincare algebra. That sounds very much like a central charge, and that's indeed the case. But today I'm just going to discuss what the flavor symmetries are. So we've already seen that the R symmetry is, it was SO4, but it takes the form of a product of SU2 times SU2. Likewise, the flavor symmetry also takes the form of a product, which I write G Higgs, GH times GC, where again, the subscripts are just kind of conventional to distinguish the two. And again, they'll refer eventually to Higgs and Coulomb. And indeed, the two factors are kind of distinguished by how the generators of these symmetries kind of contribute to central extensions of the supersymmetry algebra. So that's for next time. For today, I'd just like to describe how these symmetries are arising and what they are. Okay, so there's two symmetries, G Higgs and G Coulomb. Let me first describe G Higgs and where that comes from. So first of all, the Higgs branch symmetry, G Higgs, is something, it's a symmetry where the charged operators are kind of built out of the hypermultiplet fields, phi or xy. And kind of very loosely, it's like the symmetries of the hypermultiplet that are left over once you've gauged G, once you've kind of removed G. And so the way to say that is that if you have some if you think about some quaternion, some representation rho, it takes G and embeds it in SPN. You look at the image of that map, rho of G, and then you look at its normalizer, and then you just quotient by gauge transformations. And so this is just a concrete formula that you can go ahead and compute in a given theory, and it will tell you what the Flavour symmetry is. If the theory is cotangent type, so it's just specified by a unitary representation. I see there's a typo here. This T should be a G. Then there's a simpler formula. Again, you can just write everything in terms of this unitary representation. You take the image of G, you look at its normalizer, and then you divide by G. And that will give you the Flavour symmetry. So let me just give you an example. Just this is the easy one. Let me just give an example to show you how it works. So in this big class of quiver gauge theories, so let me just remind you what the picture looks like. It looks like this. Then the Flavour symmetry takes the following form. You take the product of the unitary groups for each of the kind of square nodes. For each of the W, remember, was the number of the kind of number of fundamental hypermultiplets at each of the nodes. You take the product, and then you mod out by the kind of diagonal U1. A very simple example is just the case of one node, and when you take the gauge group to be U1. So this is sometimes called supersymmetric QED with W flavors. So this example just corresponds to taking the gauge group G to be U1. It acts on the complex vector space of dimension W and with weight 1, 1, 1, 1, 1. So it just acts it acts with weight 1 on each of the coordinates. Okay. So in this case, if I just look at the image of U1, well, that's just the diagonal U1 inside of UW. Its normalizer is just UW itself. If I then divide by the diagonal, that's normally what we call PSUW. Okay, so that's the Flavour symmetry in this case. And then the unitary quiver example is a generalization of that. But the formula is quite general. Okay, so the Higgs branch symmetry was the easy one to describe. The Coulomb branch symmetry GC is a bit more difficult. So Jacques, maybe you could give me an indication of how I'm doing for time. I realize I can't see a clock at the moment.
Ah, okay. You've got another 20, 25 minutes.
Okay, great. That's good. Okay, so let me now discuss the other symmetry that I have in the game, which is the Coulomb branch symmetry. So we've seen that the Higgs branch symmetry is in some sense associated with the hypermultiplet. It depended very much on what representation I had, what the matter content was. On the other hand, the Coulomb branch symmetry is a bit more associated to the vector multiplet and the gauge group itself. And in this case, it's a bit more tricky to describe. And the reason for that is because really only a piece of this symmetry, an abelian subgroup, is kind of visible or manifest in the UV construction of a supersymmetric gauge theory. So what I'm going to describe for you is actually not necessarily the full symmetry GC, but just an abelian subgroup, a piece that's kind of manifest in the gauge theory description. Now, it could be that that symmetry is actually enhanced to something bigger, to some non-abelian group in the infrared. And the way that happens is that will depend very much on the details of the theory, the particular hypermultiplet representation that you choose. But this piece of it that I'm going to describe, this abelian subgroup, This piece does not. It's kind of independent of the hypermultiplet representation. It just depends on the gauge group G. And it's sometimes called the topological symmetry for the reason that I'll try to describe. And the formula for it is that it's given by the center Z of the Langlands dual of the gauge group. And so another way to say that is HOM from the first fundamental group of G to U1. So it's the dual, if you like, it's the Pontryagin dual of the fundamental group of G. So I just pulled this formula here out of the hat. And so what I'd like to do is to try to explain where this formula comes from and how to arrive at it. And the way I'm going to do that is to ask what type of operators should be charged under it. And the answer is that this symmetry, it counts monopole operators. It counts what are called monopole operators. So let me tell you what those are. So normally in quantum field theory, we might build local operators by taking, polynomials in the elementary fields together with their derivatives. A monopole operator is defined in a different way. It's defined by more like setting boundary conditions in the path integral. So what you do is you take a point P, and in your path integral, you kind of excise a small two-sphere surrounding that point. And then you kind of impose boundary conditions. You require that the fields take on a very specific form on a small two-sphere surrounding the point. And the form that we require it to take is that of a Dirac monopole. So it basically looks like a Dirac monopole, which is normally for gauge group U1, embedded into the gauge group. So the picture is something like this. If you think about the small two-sphere, and you think about two patches, kind of centered on the north and the south pole, call them A plus and A minus, then the gauge field, the gauge connection A, takes the following form. Here, theta and phi are some standard coordinates on the two-sphere. And lambda, this coefficient, this is the thing that labels the monopole. You can think of that as the kind of transition function for the gauge bundle on the equator here, or on the overlap of the two patches. And so that's a map from S1, which is the equator here, into the group G. Another way to say what that is that it's an element of the co-character lattice, which is HOMs from U1 into the maximal torus of G, modulo Wahl transformations. So again here, U1, I'm kind of identifying with the equator. And so another way to say that is that monopole operators are labeled. So you should think of this lambda as being labeled by a Weyl orbit of a co-character of the group G, or if you like, by a dominant co-character. Okay. So this lambda, all we're really doing here is we're saying that we've got a Dirac monopole, and we're taking it, an abelian monopole, and we're kind of embedding it inside of the gauge group G. And this lambda is telling us about ways to do that. Is about how exactly we're doing that. Okay, so this symmetry, this topological symmetry, it's something that's measuring the charge of monopole operators. And it doesn't quite measure lambda, but it measures basically the topological class of the bundle that's set up. So let me describe what that is. So if you think about this connection here, what it's really defining, it's setting up a connection on a non-trivial G bundle on this two-sphere. And the thing that I want to measure, or that I want my topological symmetry to measure, is the topological degree of that bundle that's set up. Okay, so indeed, a monopole operator induces a G bundle on this little sphere that I've excised. And its topological degree, which is an element of the first fundamental group of G, is just, you should think about that as just the homotopy class of the transition function, lambda. And indeed, there's kind of a projection from the co-character lattice onto pi1 of G. That's the piece that we'd like to measure, or that we'd like this topological symmetry to measure. So what does that mean? We'd like the charges, the possible outcomes of a measurement of the topological symmetry TC to give back this topological degree. What that means is that the character lattice, which is the kind of lattice of allowed charges, that should be pi1 of G. So in other words, the homomorphisms from the topological symmetry to U1, which are characters, should be pi1 of G. These are the possible charges. What that means by Pontryagin duality, by kind of flipping this implies that the topological symmetry is given by homomorphisms from pi1 of G into U1. And this thing is otherwise known as the center of the Langlands dual of G. Okay. And so the important thing to note here is that this result is, it didn't care at all about the matter that was involved. And in some sense, it was semi-classical. And that's why it didn't depend on the hypermultiplet representation. And doing things more carefully, one can in fact get an enhancement of this to some non-abelian symmetry. Okay, so that's the two symmetries that we have. Okay, before I move on, let me just give a couple of examples. So the first thing is that if I have a unitary gauge group, UV, doesn't matter what V is, the topological symmetry is just U1. And that's basically, again, the dual of the U1 factor sitting in the diagonal U1 factor in UV. Extending that example, in this unitary quiver, where the gauge group is a product of groups, then I just take the product of the topological symmetry associated to each of the factors. So in this case, I get U1 to the L, where L was the length of the quiver. And well, in fact, this can be enhanced to a non-abelian group G8, that should be GC, sorry about that, GC, which in general could be a subgroup, it could even be equal to SU2L plus 1. And that's no coincidence here. In fact, the SU2L plus 1 here is the kind of, well, its Lie algebra is associated to the, its Dinkin diagram is the shape of the quiver. And that kind of gives the maximum, the largest possible thing that this can be enhanced to. There doesn't always have to be a topological symmetry. For example, if the group is SU, a special unitary, then there's no topological symmetry. The answer is empty. The topological symmetry also doesn't necessarily have to be continuous. It can also be discrete. So for example, if the gauge group is SO3, then, well, the Langlands dual is then SU2, whose center is Z2. And so there's a Z2 topological symmetry. So it can be continuous or discrete in general. And the same goes for the Higgs branch symmetry. Okay, so these are my two symmetries. So, so I'm coming to the end of my talk. I suspect that I'm a little early. I hope that's okay. I'd be very happy to take questions, but let me just summarize then what I've said. So a 3D n equals to 4 gauge theory, it's labeled by two pieces of data. There's a gauge group G, a compact Lie group. We have to specify also a quaternionic representation, which specifies the kind of matter content. And theories of this type have the following global symmetries. There's an R symmetry, which is SU2 times SU2. And there's also a Flavour symmetry, which is GH times GC, which is also a product. The R symmetry is always SU2 times SU2, but the details of what the Flavour symmetry is will, of course, depend very much on this data, these two pieces of data that specify the theory. Okay, so that's a summary. Let me tell you what's happening next time. As I've already alluded to, next time I'll tell you about central extensions of the algebra. And that's very much connected to these two Flavour symmetries, G Higgs and G Coulomb. And what we'll do is we'll introduce kind of parameters associated to those symmetries, which are called mass and Fi parameters. And you should think of those as deformations of the theory. And one of the things that we're going to be interested in these lectures is how the space of vacua depends on those parameters. And so we'll talk about supersymmetric vacua, how you build them given this data, and how they depend on the mass and Fi parameters. So you imagine varying these parameters, and you can ask how the supersymmetric vacua depend on them. Much of that can be framed in terms of studying kind of domain walls between vacua. So we'll discuss those as well. And that will lead us to study kind of, well, walls and chambers in the spaces of these parameters, which is kind of the beginning of seeing structures associated to representation theories. These things will be like root systems, if you like, for Lie algebras. And so we'll start to see some representation theory data coming in there. Okay, so that's all I have to say. I'm very happy to take questions.
Okay, thanks very much, Matt. I think at this point, I'll just ask people who have questions to raise their hand, and I'll unmute them.
I can see some questions in the chat, but
yeah. Did anyone in? Oh, there's one at the end here. Ajit, do you want to unmute yourself and? Let's see.
I think one of us has to unmute.
One of us has to unmute him. Okay. Which it makes it difficult because raise your hand and then I'll be able to see you.
Hello?
Yes.
How does that lambda fit in A plus and A minus? Where are they taking values really?
A plus and A minus. Where did that appear in my talk? I can't remember.
That was in your description of the monopole.
Yes. Ah, so here. Yeah, so here, sorry, A plus and A minus are so they're the kind of they're the background, they're the connection, the gauge field on each of the two patches of the hemisphere. Okay, and so lambda here, well, there are a couple of ways to think about it. You can just think about it as in some sense as like a weight, a co-weight or a co-character. So it's just a bunch of integers. Or you can also think about it as a transition function. It's kind of telling you the transition function between the gauge connection on the two patches of the sphere. Okay.
Matt, I have a question. I seem to not be able to figure out how to raise my hand, so I'll just go ahead and ask my question.
Go ahead, yeah.
So you were talking about the enhancement of the topological symmetry to a potentially non-abelian symmetry, right?
Yeah.
So whether that happens or not is fixed by the data G, the representation.
Yeah.
It's just that it may not be transparent in the Lagrangian description.
That's right. Yeah, it may not be transparent in the Lagrangian description. You know, I think the honest answer is that the symmetry only really appears in the infrared.
And so when the topological
I mean,
symmetry,
sorry, go ahead.
yeah, sorry. When the topological symmetry is continuous, like one of those examples where it was U1 to the rank, in those cases, is the rank preserved in the enhancement, or is that not guaranteed?
That's a great question. I thought that the answer was yes, that the rank is always preserved, but I remember Ami telling me once that that was not the case. And so you may,
okay.
He knew of examples where the rank could be increased in the enhancement. But yeah, my understanding was this, that when it's continuous, you know, it's the maximal torus of
yeah, the non-abelian one.
Yeah,
right?
but maybe, yeah, but that would be, we should ask Ami if there's an example otherwise.
Well, we'll pin him down later in the conference.
Yeah, thanks for the question.
But did I cut you short? You were going to continue to say something.
No, that's fine.
Okay.
Well, yeah, I mean, especially to the students, if you have any questions, I'm really happy to answer them.
So Kirsty has an example. Feel free to message me on Slack. She doesn't wish to share it. Okay.
Great. Let's have a discussion there. Yeah.
That would be great. Okay. Well, we managed to finish early. And so the next talk will be in a half an hour. Okay, at 11:30 US Central Time. You'll have to do the conversion yourself to your local time zone. See everyone then. I'm supposed to post the MetaStream link again. Let me do that because the next talk will be on MetaStream. Let's do this. And I have half an hour to figure out how to make that work smoothly. So see you all in half an hour. Very good. Thanks a lot, Matt.
Yeah. Thank you, Matt. And